This is the first installment of Grodsky's Last Stand, the crash course in chemistry, Unit 1, Atomic Structure. I'm going in the order of how these questions appear on the New York State Regents, and I'm covering exclusively New York State Regents material. Okay, and this is designed for you to review the course, not outside of what your teacher is doing, if I'm not your teacher. Okay, but this may prove to be helpful in your review, so let's go. So we're going to start with atomic structure and the models of the atom which you're held accountable for. It all began on a cold winter day. No, I don't know what day it was, if it was winter, but the early Greeks, okay, we're talking about before BC, around 500 BC, began the idea of this small pieces of atoms, or how the matter had its structure. And Democritus was the first Greek philosopher who believed in the indivisible theory, that if you took matter and you cut it into smaller pieces, okay, you'd eventually come up with a particle. And he coined the word atomos. Atomos is indivisible particle. So atoms had its birth, at least its name, from the idea that there are small little things that make up all pieces of matter. Aristotle, okay, came a little later to the scene, to the party, and disagreed and came up with the divisible theory, meaning matter could be cut in half into smaller and smaller pieces, cut halves of halves of halves, and you would just get smaller pieces of matter, not particles, or you wouldn't come up with a particle that made up all matter. Okay, and that permeated for over 2,000 years, okay, or at least more than that, 2,000 plus years. That philosophy of no particles making up all matter, or at least the idea that matter was continuous. Okay, John Dalton, an English teacher who studied science, okay, came up with the first modern atomic theory. He outlined elements as, in his theory, as something made up of the same type of atom. So he brought back atomos into the modern era. This is late 1700s, early 1800s, and elements are made up of the same type of atom, okay, the same atom. Didn't know how they were the same, okay. Compounds were made up, or in chemical reactions, from elements or atoms from one compound interchanging with others. So if this is one atom and this is another, and they reacted with another atom like this that looked something like this, like cross eyes, they may make something that makes something like this, and another one that looks something like this. So atoms are just rearranged, okay, and this of course are compounds, two or more different types of atoms. So how the atoms differed is something he didn't know about, but he came up with a model. So the Dalton's law, or Dalton's model, okay, was a solid sphere. Why not? You put your hand outside a window, your hand hits gas molecules, your hand moves back. These particles are hitting your hand, so a solid sphere is how Dalton, of course, among many things that he did, saw how atoms were. J.J. Thomson, using the cathode ray tube, so the cathode ray, notice if you just learned redox, the cathode ray tube, electrolytic cell, okay, electrons are coming from an anode, okay, to the cathode. The cathode, of course, is negative. But in any case, in a cathode ray experiment, he discovered electrons. Okay, J.J. Thomson. And his model, okay, was still a solid sphere, but you had these electrons that were just kind of, as some would say, plums in a plum pudding. So you had that plum pudding model, okay, where electrons are just kind of haphazardly in the sphere. Now, in this plum pudding matrix, you have positives that are smeared, not, I shouldn't say protons, but just positive charges that were filling in this empty space here. So we'd say there was a matrix or a glue or a pudding that was positive, smeared all over, and the negatives were likewise smeared all over, and they were in the sphere like plums in plum pudding. Okay, so here's the plum pudding model sometime. Plum pudding model of the atom. All right. Now, Rutherford, with his famous gold foil experiment, he shot alpha particles, and you guys should know now, alpha particles are 2 protons and 2 neutrons, a helium nucleus at, okay, at gold foil, very thin, okay, nucleus, or very thin piece of gold, a few atoms thick. I'm just going to draw 1 atom thick. And when he shot these particles, most of them went right through. When they got close to the nucleus, they deflected away, okay, which led him to believe that the nucleus was positive. The nucleus is what Rutherford discovered. He discovered that these positives that J.J. Thomson thought were just basically in this matrix all over the atom were confined to a small part of the overall part of the atom. So the nucleus was small and it was positive, and all the mass of the atom, so it was small, positive, and dense. And he said that the atom is mostly empty space. That's why his particles, his alpha particles, went right through. Only when they got close, they deflected, and once in a while, they would bounce back. So he discovered that these positives were not all over the atom. They're in a small, dense center, and the atom is mostly empty space. So his model of the atom changed from J.J. Thomson's into one where you had a nucleus, okay, positive nucleus, and electrons that were negative were outside that, okay, something like that. And along came Niels Bohr. Now Niels Bohr organized these electrons, and I'm just going to erase this, into organizational shells. He made these shells, okay, where these electrons exactly had to be. He had the planetary model, right? So his planetary model was electrons existed in distinct energy shells, which are principal energy levels. So this was the first energy level, the second, and the third. And we learned very quickly electrons that could exist farther away had higher energy than electrons that were closer to the nucleus. Why? Because electrons are negative. They're attracted by the protons in the nucleus, or the positive part. How can they exist farther away? They have to have higher energy. So to go from, let's say, a leap from the second to the third, atoms need to gain energy to overcome the positive pulling force. So you need to know. So if I have these shells, make it bigger. Here's my nucleus, and let's say this is shell number 1, 2, and 3. For an electron to jump from its low energy state to its higher energy state, it needs energy to overcome the positive pulling force. So electrons move away when they absorb, but when they jump back, okay, they emit energy in the form of light. You'll hear that word spectra. And that light that's given off can be measured for energy. Roy G. Biv. Okay, the violets have higher energy than the reds. And these leaps are called quantized leaps, or quanta. So what Bohr did is he took the atom and organized the electrons according to specific energy levels. And these energy levels are called quanta. So he quantized the atom. He put the atom, okay, and organized it and explained for the first time the spectral lines of hydrogen, okay? And we were into something called the quantum revolution. Why energy is not in discrete, or not, I'm sorry, energy is not continuous. It's in discrete energy levels, discrete bundles. And what's discrete about quanta is you have to have exactly enough energy. So if an electron wants to get to the second level here, it needs exactly enough energy. If it doesn't have enough, it stays where it is. Kind of an all or none response. But in any case, he had a planetary model. Okay, explain the movement of electrons with the energy emitted and absorbed by atoms. Okay, and of course he was able to explain the spectral lines that you guys saw in the gas tubes. And from this work, you know, we understood the atom much better. However, it had some limitations. He could only explain hydrogen. Okay, so certainly a lot more elements that he could not totally explain, but his ideas, okay, led us to the current model called the quantum mechanical model, sometimes called the electron cloud. Okay, so electrons do not exist in circular paths and orbits. By the way, 1, 2, and 3 would represent the rows on the periodic table. So even though we talk a lot of times about shells of electrons, Okay, a lot of times we'll go back to the Bohr model to make some sense of this because it's hard to think in terms of quantum. But what you need to know is the electron cloud model is that electrons existed not in orbits, but in shapes. Okay, so they would be electrons. We didn't know exactly where they were, but we could say with a probability is a word you'll hear, where they are in this shape. And we have also, okay, shells that are farther away. Now they're not circular orbits, but they are in a different shape, electron cloud. You notice to go from the blue to the red, you would need discrete amount of energy, so the same ideas. So instead of orbits, to give Bohr credit, they call orbitals. So electrons exist in orbitals based on probability, and the biggest one is that we're going to treat the electron not as a point charge, but as a wave. It's on this wave or mechanical model is that electrons are behaving more like a wave. And sometimes you'll hear the wave particle duality. And that's part of the quantum revolution, duality. Okay, electrons behaving as in a wave and as in a particle. Okay, and that's our current model. That's the basics you need to know. So probability, orbital, electrons acting as a wave, you know you're dealing with the current model of the atom. Okay, let's continue. All right, so now we're at the point where we're going to talk about the actual protons, neutrons, electrons. Okay, and I'm sticking to the Regents curriculum here. So we look at beryllium. Okay, beryllium has an atomic number 4. And again, on your reference table, or your periodic table, atomic number is there. That's the big number on the bottom. Okay, it's the number that identifies the element. John Dalton stated that all elements have the same type of atoms. That's true. We now know what makes the element beryllium beryllium.
All AP government students, please report to the LGI for your exam, and all AP French students, please report to the library for your exam. Again, at this time, all AP Gov students and AP French students, please.
Okay, so how do we figure out how many protons, neutrons, electrons? The first thing is to notice that this bottom number, the biggest number is the atomic number. All elements are unique by this number. So this tells me how many protons. Okay, so in the nucleus, protons, the number of protons identifies the element. They're very important. This proton number is not changing unless you are dealing with nuclear chemistry equations. All right, so this has 4 protons, the most important one. All the other parts of the atom, which we now know are electrons on the outside, protons on the inside, and neutrons on the nucleus as well. Okay, it's about the protons. What makes lithium lithium? 3 protons. Okay, so if you want to know a symbol of an element, find its proton number. That's not going to change. Okay, it's very important that these things are linked. Okay, symbol represents the proton number. So for beryllium, it has 4 protons. Now, in the periodic table, atoms are always neutral. So they're always written neutral. Don't fall in love with this charge. So this is also 4 electrons. Okay. Why do I know? Because if this is neutral, I'm +4 in the nucleus, sometimes called a nuclear charge. Okay, I have to have 4 electrons in the outside. So beryllium has 4 protons and 4 electrons. This number tells me protons first. If it's an atom, if you hear the word atom, atom means 0 charge, which means protons equal the electrons. This bottom number is also electrons. All right. Now the top number here is the mass number. What gives the mass of a element is, as Rutherford found, is what's inside the nucleus. What's in the nucleus? Protons and neutrons. Electrons seem not to have much of a mass. In fact, electrons are about 2,000 times lighter than a proton and a neutron, and a proton and neutron have about the same mass. Now, if you forget this, there's a place to go. Here's that place, table O. Look at here for a second. Now, the beta particle is actually an electron. So there's an electron. It has a 0 for a mass. Top number is the mass number, just like periodic table. The bottom number is the charge number. You could think of it the proton number, but it's really a charge number. So electrons are -1, have a mass of 0. Neutrons have a mass of 1. They have no charge. Protons have a mass of 1 and a charge of +1. So neutrons and protons have the same mass. Electrons are so small, they're 2,000 times lighter, they're considered to have no significant mass. All right, so if we look at calcium, let's do another one here. Calcium has an atomic mass of 40.08, and it also has an atomic number of 20. That should be able to give me how many protons? That's right, 20 protons. How many electrons if I say atom? And you would say 20 electrons if it's an atom. Protons have to equal electrons, and you know this in redox. Standalone elements are 0, aren't they? Why are they 0? Because the protons equal the electrons if it's an atom. Now, how do we get neutrons? Didn't talk about neutrons. Neutrons have a mass of 1, and so does the protons. So this top number is the proton number and the neutron number, and this is the proton number. So if I go here, go to calcium, let's round that to 40 and make this 20. We get 20 protons, 20 electrons, and to get the neutrons, we subtract 20 neutrons. Why? This is the protons and the neutrons. They have mass, and this is the protons. Subtract, and you get the neutrons. Okay? It's very important. It's an atom. Okay? Atoms, these guys are equal. These won't always be the same. So let's go back to our table. And now we're going to deal with ions. Ions are not atoms. They have a different charge other than 0. So how do they go from 0 to a charge? Well, first of all, upper right hand corner tells you the oxidation state. That's a charge that they love to become. So when boron is an atom and becomes +3, how did that happen? Well, you guys know from learning redox that my charge just went up because I lost negatives. I do not lose protons. If I'm boron +3, that B means what? 5 protons. So if I'm boron +3, I still have 5 protons. That means I'm +5 in the nucleus. My nuclear charge is +5. Well, how do I become positive or negative? It's because of electrons. So my friends in chemistry, to become +3, I had to lose 2 electrons. So how many electrons does boron have? And you would say boron has, well, it starts out with 5 electrons, doesn't it, when it's an atom. But when it becomes +3, okay, it must be losing 3 electrons. So boron has 2 electrons, 5 protons, okay, of course 10 minus 5 is 5 neutrons, okay? So when I ask you, or they ask you how many protons or neutrons or electrons, be careful about atom or ions. Same thing with aluminum. Notice it's in the same family. They have the same, what? Valence electrons, therefore they become the same charge, but different unit, but it's all attached. Aluminum, how many electrons does it have when it becomes aluminum +3? Or when it becomes an ion, since it only has one choice? Well, it starts out with 13 electrons, and when it becomes positive, it loses 3. So it starts out with 13, and now it's down to 10 electrons. You lose your negatives, you become positives. Okay, and if you look, if we get smaller here in the periodic table, we look at our non-metals versus our metals. You should know in this area here, these are all our non-metals. And this area that I'm drawing next is all our metals. And metals do what, guys? They're big radii. They become positive, okay, by losing electrons, which we call oxidation in redox. Okay, so in any case, if I said to you, how many electrons is in Cl -1? Okay, well, you'd look up your chlorine. Okay, we'd look up our chlorine. And we'd say, okay, chlorine had what? 17 electrons, 17 protons. What's an atom when it becomes -1? It has one more than normal, so it's 18. Okay? It's very important you understand what happens there when you become an ion. Now, electrons can change to become ions. Okay? Neutrons can be different to become isotopes. Isotopes, very important word. Iso means same. So isotopes are the same element, therefore the same proton number, atomic number, but different number of neutrons, therefore different mass number. Notice these are the 3 isotopes of hydrogen. To get neutrons here, okay, this is 0 neutrons. 2 minus 1, 1 neutron. 3 minus 2, 2 neutrons. They all have the what? They all have the same proton number, so they're all protons of 1, therefore all hydrogen. So they all have 1 proton, but different number of neutrons. They're a heavier or lighter form. And as we saw in nuclear chemistry, some of these are actually radioactive. So it's nice, you have to know which isotope. So anytime you see an element, they say H1, or they say hydrogen -3. The number they're giving you is the mass number, because it's important to know which exact element you have. All right? If you have hydrogen, they're going to know what isotope. Every element has multiple forms. What makes it unique is the proton number, but sometimes these elements have more than one type of neutron arrangement. And we want to know exactly which isotope. So don't fall in love with the fact that this is going to be your answer. A lot of questions will have a dash and a 3. You've seen this. Carbon what? 14. Why they give me the 14? Because which type of carbon do we have? This one's radioactive. Carbon 12 isn't. So from this point forward, an element with a number is telling you the mass number. Indirectly, they're telling you the neutron number. So identifying isotopes are very simple. Same element, different mass number, different number of neutrons. There's more to this though. Okay, what's more to this? Well, this number is what? It has a decimal place. How come it's not 12 if every neutron is 1? Okay, well, this decimal place is due to the averaging of all the isotopes for carbon. Now, if you average all the isotopes and their relative abundances in nature, you're going to get an average that's closest to the most abundant isotope. Carbon 12 exists about 99.9% of the time. So the average is going to be closest to that number there. Nitrogen 14 occurs again, the most abundant isotope most of the time. That's why that number is closest. So anytime they ask for the most abundant isotope, look for the number it averages into. What's the most abundant isotope of boron? 11. Now, how do they come up with this average? Do something called a weighted average problem. We'll do that next. Okay, so let's look at a example of a weighted average problem. So we have carbon 12 and carbon 14. Okay, and I want the weighted average. Okay, so let's pretend, I don't write this 6 here, by the way, because it's implied with carbon, it's definitely 6, but we'll put it there just in case. Okay, so I want the weighted average. Okay, let's pretend that 90% of all the carbon in the universe exists as carbon 12. Let's also pretend that 10% of all the carbon. Okay? Okay, so what we're going to do now is once we know the relative percentages in nature, we're going to average them using those percentages. So I'm going to take 90% of 12. 12 times 0.9, and I'll come up with that answer. And then I'll take 10% of 14. So 14 times 0.1. I know that answer is 1.4. And I know 12 times 0.19 is 10.8. And what I do with these two numbers is I add them. 10.8, 1.4, 8 and 4 is 12. And then, of course, 10 plus 1 plus 1 is 12.2. And my new isotopic mass is carbon 12.2. Okay, and that's where the the decimal places come from. by averaging up the isotopes, same element, different mass number, but using their relative abundances in nature and using their weights. So 90% of all carbon is carbon-12. It makes sense that this number would be close to 12. That's why if you round carbon-12, you will get the most abundant isotope. Carbon 12.2 rounds to carbon 12. And that's why the most abundant isotope can be obtained by looking at the periodic table and rounding the number. Okay, last little piece here is electron configurations, because we know that elements, okay, go in order of atomic number, protons, but they also follow a rule in terms of electrons. Okay, if I go to my periodic table, okay, that I've been marking up here, okay, if you look very simply, okay, if we look at the periodic table, we'll see that this is the first shell. 2 electrons exist. The second is 8 electrons. Okay, and all we need to do here is look at the configurations given to us by the reference table. That number below 2-1 means there's 2 electrons in the first energy level and 1 electron in the third. These are called ground state configurations. Beryllium's 2-2. Okay, going across the periodic table, boron is 2-3. We're filling in that outermost valence shell. Now the valence electrons are those electrons that are not in a filled valence shell. This 2 is filled. These are core electrons. But boron has 3 valence. Carbon has 4 valence. Notice it equals to this last number here. And that's 5 valence. So valence electrons are from electrons that are not in a filled energy level. But these are all ground state. Now notice something here. Okay, the noble gases, they don't have valence electrons typically. They show 8, but they don't have valence electrons because usually they're filling their second energy level. So that's why they're stable. We'll talk more about that in another unit. So these are all ground state configurations. But we have something called excited state. So in the ground state, fluorine is 2-7. Now, that's when electrons fill from lower energy levels first. But what if an electron in the second energy level gained enough energy, absorbed energy, and became 2-6-1? Now it's going out of order, and now we have an excited state configuration. Notice it's still fluorine because we didn't lose the electrons, so all of the what? All of the electrons will equal the protons still. So if I ever say to you, hey, who's the excited state of fluorine? Remember, that's 9 protons, 9 electrons. So if you count with me, 6 plus 2 plus 1 is still 9. Electrons are going out of order because of an excited state. Okay, we've learned that if you add energy, electrons jump away. So this is an excited state going out of order. This is going in order, called the ground state. All right, and that's the major pieces of atomic structure. Okay, becoming an ion, losing and gaining electrons, isotopes, okay, configurations. Now, one little thing I didn't talk about, to know the max amount of electrons that exist in each of the 4 energy levels, you can do the 2n² rule. So if I'm in the first energy level, that's the first row, or the first principal energy level, which is the first row in the periodic table, well, 2 times 1 squared is 1, times 2, there's 2 electrons. If I'm in the second energy level, the second row of the principal of the periodic table, 2 squared is 4, 4 squared is 8, okay, I'm sorry, 2n², so this is 2, 2 squared is 4, 4 times 2 is 8, and 8 electrons exist. So we get 2-8. What about the third energy level? Well, 3 squared is 9, 9 times 2 is 18. And how about the fourth energy level? 4 squared is 16 times 2, 32. So these are the maximum amount of electrons that can exist in each of the 4 major principal energy levels. But again, if you forget, you can look and zoom in on your periodic table that shows you these things, okay, by looking at the numbers and how they fill. 2-8, 18, here comes a 32 eventually. We'll get there. Okay, there's a 32, so it tells you that. And those are the major points of Unit 1 atomic structure.